Hello, it's Mr. Joseph, Machine Learning Associate, Researcher and Student at Makerere University, presenting to you a project titled as follows that aims at solving a problem that originates from the fact that various microfinance institutions in Uganda operate out of formal credit bureaus and have high portfolio at risk because they have no data-driven decisions to make loan decisions. And some of the key terms that we shall be facing in front there. Module 1, we mean this provides credit risk scoring. And module 2 provides monitors the loan disbursement. This one, XGBoost, is a model. Sharp is a mechanism we use to explain every decision that our model makes. And then area under precision recall. This is a metric that we use to overcome the class imbalance problem. Then group shuffle split is a mechanism we use to prevent SACO data leakage. And then we have various works have been done in this area. The first one being logistic regression that requires formal credit history that are not available in London circles. And then the second one does not carry out to shuffle splits, therefore there is leakage and it does not generalize well. And then the first one, it's very unstable on small circles in Uganda. And then this one, the fifth one has no sharp explainability, which our regulations requires. And most of those challenges, we handle them in our project through the group shuffle split. And then, yeah, so progressing, the key of the problem is that most of the loans are granted out of feelings, and then also the loan officers lack ability to know if someone has defaulted somewhere else. They're coming here, and then they also just are shocked with loans getting into default without even them getting early warnings. And then also we have challenges in class imbalance, whereby majority of our target variables have majority of it being the false and then a few being true. So we have to handle that carefully. And then we have institutional leakage, where we talked about that thing. We handle it through group shuffle split. This is where like data from one given institution falls in different partitions of the train, test, and validation. This promotes the leakage, which we handle through this joint split. And then we had several objectives of carrying out to exploit data analysis driven by the question framework, then design, training, and evaluating 8 machine learning model architectures, of course, deploying the model for availability. And then we had questions we aimed at answering in our research. So the objectives, fulfilling those objectives, definitely rolled out into our contributions in this particular project, whereby we successfully carried out the exploratory data analysis. We compared the models we have deployed, and then we have also established the 3 deployment phase plan, and we are on phase 1 as per now, which is the the hand-in-hand working with the loan officers. The model makes the decision, but the officer does not alter the decision. We just log the decisions and check the S metric. So this here we present the pipeline of our process, starting from data ingestion through feature engineering, training, leakage, then we carry out the model selection here, basing on stability RAM, then we do our compression, then we deploy. So here we are indicating just the detail of the module 1 pipeline, including even the features it inputs, and then also the knowledge distillation and its API that it exposes. In this threshold, we clarify that in module 2, we have its architecture specified, but the training and evaluation have not taken place. So progressing here, this is just a high-level overview of how our system interacts with the external system. So we receive the calls, then that comes to our loan gatekeeper, which gives the risk, then low risks, low loans, go into running loans and then up to the end. And then also this is the Sanskrit pipeline that we have used during our model training. So we use specifically median imputer to fill in the missing value for numerical columns, and then robust scalar. We prioritize it over standard scalars. Why? Because of the outliers that our EDE exposed, extreme outliers, and then one not according to create the binary columns that the XGBoost classifier clearly understands. So diving into the models that we evaluated the 8 of them, starting with the XGBoost, which managed to be like the best model for this. Say this model here, for it builds the tree incrementally, but each tree aims at refining and correcting the prediction of the previous tree, because given tree will not be 100% correct. So it is composed of the objective function. This function is the main goal of the model, but the model doesn't aim only at being correct, but it's also aiming at being efficient. That's why it has this regularization function, training loss function. Then this regularization function is comprised of the penalties that the gamma and the lambda presents, and so those penalties are offered for every extra tree that the model. This is the pre-update function, which comprises of every previous predictions of all other trees, and then the prediction of the current tree that is standardized by the learning rate. So and then we handle the class balance through scale pose weight, whereby it gives us these are the non-defaulters and these are the defaulters in the train data only handled. So the 3.26 implies that we should penalize the model 3.2 times higher when it misclassifies the default than when it misclassifies a non-default. So progressing through other modules, so we look at logistic regression. This one for it, what it does is it computes the weight of future inputs. It computes the weight of the sum of the weights of the future inputs plus the bias, and then passes it through a sigmoid function 1 plus e to the power of exponent negative z to generate the default probability. And then random forest for it is a committee of multiple trees whose decisions are later summed and the average is gotten. So basically, the final output of the probability is the average of the decision probability, the probability output by each tree. And then CatBoost for it, we look at it, for example, for a categorical feature like a district. What CatBoost will do is, what for it will do is, it will get the default rate of that borrower basing on that district, but basing on only the records that existed prior on. So that one, in that way, CatBoost prevents leakage, prevents the model from peeping into the feature by not using the current record. And then LightGBM for it builds the tree by splitting the branch that benefits the model the most. So what it does, it also discards off the simple example so that it will put much of its effort on the hard examples that improves the efficiency of the model. By this way, it manages to be super fast. So EBM, what it does is it learns the simple curves for each specific feature and also the pairs of feature. Now, in this way, and then later it sums all of them together. And then in this way, it provides ability for someone to derive graphs for each of the feature and then get clear definition of why the model is predicting whatever it's predicting. So we have tabnet transformer. So tabnet through its let's say sequential attention. So what it does, it selects a given feature set to concentrate on for a particular borrower at every particular decision point. So in that manner, it selects a different one, and it does that through a given mechanism of the sequential attention mechanism, and so the Sparse function. And then we have the tabnet transformer. This one for it it converts the categories into values, and then make sure the categories, they look at each other, look at other categories in the same records. So in the same record data, such that these categories will update its values in relation to those previous what? I mean, in relation with those similar what? Categories. So in that manner, this ensures that the categories interact among each other and captures the relationship that exists between the different ones. Then we have the decision tree. This one is just a small model, lightweight model, that basically for it learns from the soft labels of the teacher model, as we did in the distillation process. So we progress to data description, whereby we had over 9,000 records, and the variable categories as listed below, and then all other personal identifying information, we hashed them throughout, and then we had data quality issues, of course, but we engineered the target variable with strict conditional rules after engineering, but we still had a class imbalance of 3 to 1, and clearly shown by our visualization here, whereby the fully paid outnumbers the all these other categories, which falls into the defaults. So we also have the relationship, which shows us duration default. It's not overly monotonic, but it gives us a clear correlation, whereby loans that are borrowed for few days have low default rate, but those ones with high, as the default, I mean, the days increases, the default rate also increases. So then we have the loyalty effect, whereby you can see first time borrower have high default rate for the first loan, and then those ones who are borrowing for the 6 labeled in green, they have very low default rate. And then we also captured the what we call as school fees effect, where in month where students are about to go back to school, the loan number, people borrow a lot of loans, and also the default is high. This one gave us insight to label, to engineer a new column as is school fees months column, which has a very high sharp explainability value. So looking at the results, that those models that we did validation on which we did the threshold tuning to get the actual threshold. Focusing on the test leaderboard here, we look at the Brier score, which is telling us how well a model is predicting the probability of a given defaulter in relation to the actual outcome. So we look at if we look at our base here, our base default rate, we look at some of the models are really performing bad, because if we use a special function, which I will demonstrate if I had time, we get a base Brier of 0.21, approximately 0.21, and some of the models are just approximate to that. That means they are really performing bad in predicting the actual probability. But these models like XGBoost are far lower than the base Brier that can be generated. So we also have matrix area under precision recall, which measures the prediction of a given model at different threshold. Given we keep on changing the threshold, how well will the model perform? So these models indicate for us, if we use the base, which is from our test database default here, we find out that our models are performing 2 times better than just a random model that would just predict everyone as maybe non-default. So it's 2 point something times better than that. So we look at how well our model can also differentiate between default and non-default, and this high probability are indicating for us that if we focus on, let's say, XGBoost, which is our winner model, that we are looking at it 0.76 times, this model will give high probability to a defaulter than it gives to a what? To a non-defaulter. So we said we selected our model based on shuffle split basing on those other metrics. To come back again, we basically relied on F2 scores, which weighs precision, recall, more time than precision because of the class imbalance issue. And therefore, we focus on those specific metrics to determine the best winner. So we do 6 split, random split. And in those 6 splits that we do, we get the average of everything, the average of standard deviation. Then the one with the least average of standard deviation is the most stable model, and it emerges as the winner. So we also conducted explainability, because the regulation requires us to do, and we used kernel explainer with link identity, and then we used the 200 sample test data, background test data, to act as reference for our kernel explainer. And then we also use the 500 test data to generate this kind of artifacts. And this one here is showing the average impact that a given feature has on predictions. And then this BSWAM here is showing us the impact of a given feature on every prediction. The dots are predictions. The red is showing you a negative impact, and the blue is that the feature had a positive impact on that particular prediction. So we have the waterfalls here giving us why a particular loan was rejected, and here why it was not rejected. And then afterwards, we serialize this and put into deployment to generate explanation for our users. And then in the model selection, as said clearly, that in selection, what we are doing is we selected basing on stability run, and then we expose these endpoints for the users to access. And then we are still in shadow mode of the deployment phase. So whereby they work hand in hand, but no decision is ever altered. What we are doing, we are capturing the KS, whereby so then we progress to model compression for performance purposes, and so we generate a simpler model with a simpler architecture, which mimics the teacher model, uses actually the entire logic of the teacher model, and it performs almost like the model. Why? And we choose knowledge distillation. Why? Because it preserves the complex logic. It's not all about removing the features, but also it also has the architectural simplicity through the dark knowledge. Dark knowledge, what do we mean? We mean when we use the T, we expose the relationship that exists between the teacher's prediction. Let's say if the teacher predicts 0.9, so when we divide, we reduce that value and increase the other 0.1. Now it reveals clearly the relationship. Now next time the child will learn that actually this defaulter looks somehow like non-defaulter. So that is how the dark knowledge is transferred. So this is the process whereby we reveal the hidden relationship, and then we strip the sigmoid function, and then here we create the expert device, as I was talking about the dark knowledge. So this is the pipeline of knowledge distillation, where we do the same identical pre-processing pipeline like the science kit, which I talked about later on, the one for the teacher. Also the same for the student, and then we establish the teacher's baseline against which we shall be using to compare. And then afterwards, we generate the soft labels of the teacher, which the student will learn on, but then we continue, we first blend it, whereby we're calling it loss blending. We don't want the student to just cram the result from the teacher. Therefore, if we say alpha is maybe 0.8, we are saying get 80% of your knowledge from teacher, but also 0.2% of your knowledge to come from the real world situation, the true values 0 and 1. So then afterwards, we train the student, then we evaluate them, whereby here against we evaluate them against their own base, the teacher's base, and then their actual distilled values. But the actual ones, which can give you a clear insight here, we look at the one that has the most gains. I talked about these metrics, and that is the student that emerges as the best. As per our outcome, we have the student doing 121% performance rotation, and traditionally we don't expect this, but well documented references, this is very possible situation whereby if there is in label smoothing, whereby the student lands on the soft labels rather than the rugged zeros and ones, and also whereby the student acts as a knowledge distillation, maybe acts as regularization, whereby now we have few number of trees, don't form complex rules which will just bring noise. Like the trees decision tree only used six trees only. Therefore, the student will just learn from the soft labels and not create complex trees. So with that, the noise were filtered and removed, soft labeling happened, and our student managed to actually achieve 124% retention. This is our product interface, which the users are working with for demo purposes, but we provide full API for access. Yeah, so we have some of the limitations we had in data quality, and then also we never looked at macroeconomic features like inflation that would happen, and then geographical institution focus, whereby more institutions that are in different geographical locations or economical conditions, the model may perform slightly different. So, and the class imbalance issue, of course, gives us much difficulty whereby our model do not achieve the maximum scores that are intended due to this class imbalance. So in conclusion, we look at this is the first disjoint leakage and audited model that we have in Uganda, and then these are the things that our EDE reveals, that the loan that are marked as excellent, I mean collaterals that are marked as excellent are actually default the most. And then we are in our future works, we intend to do further data collection to resolve those null columns and what, and also do the neural network models, their performance. We intend to put the USSD. Yeah. And then, yeah, these are the references for our work and some of the acknowledgements. Yeah, thanks for listening. I mean, Mr. Joseph.